Okay, and we're going. Okay, so here's where we were last time. We were talking about polar coordinates. Remember, a coordinate system is a way of using numbers to identify where you are in the plane or in space or something like that. And we're accustomed to the rectangular coordinate system, but there are others, and so we're starting off here with polar coordinates. Again, defined, roughly speaking, by this picture, which again I encourage you to think of as a function. That's going to be particularly important later on in chapter 5. So details, issues about uniqueness, and notation. And here's where we left off. So these formulas, easy to write down from the trig of the picture that we just looked at. Tempting, though, to try to then solve for r and theta. It's tempting to write, for example, and I'm going to write this down and then cross it out quickly because it's importantly not true. But anyway, here we go. Forgive me. R is, let me go ahead and cross it out anyway. Square root of x squared plus y squared. Right? Very tempting to write that. I mean, isn't it, right? If r squared is that, then isn't r the square root of it? Also tempting to say theta is, and again, I got to cross that out. I don't want to accidentally write down something false here. Arctan of y over x. Very tempting. So here's the problem with these formulas here. This first one here suggests that r has to be positive. This symbol here, right here, means the positive square root. Right? And there is no such rule. R does not have to be positive. R can absolutely be negative, no problem. Asterisk, there's going to be some issues when we get to integrals. But for the moment, R is perfectly allowed to be negative. So you just can't assume R is going to be positive. Likewise, this formula here, arctan, well, arctan always takes values between negative pi over 2 and positive pi over 2. And it is just not the case that you can assume theta must be between those values. Just not true. So anyway, don't step on that landmine. This is an easy mistake to make. So rather, I encourage you to just use these formulas that I've got written down here and geometry. Right? Make sure you understand the geometry of the picture, and yes, use these formulas. And then use that combined with the geometry of the picture should tell you what the actual values are. So here's my example. Let's think about this point right here. -1, there it is. And let's think about the polar coordinates for that point. Now, you can take this and plug it into these formulas, and what comes out is that r squared is 2, and tan theta is 1. And from that, you can pretty readily conclude that, let's just use, that r has to be one of these numbers. Which one? Yet to be determined. I don't know. We'll think about that in a second. And theta should have to be, I'm going to loosely say pi over 4 or 5 pi over 4, one of those numbers. Why am I humming and hawing on this? Well, of course, you can always add any multiple of 2 pi, and it's still go in the same direction. So yes, technically theta could be a lot of different values. So, okay, true, but it's always true, and so therefore it's not that interesting to talk about, right? So let me, for the moment, just focus on the pi over 4 and the 5 pi over 4. Okay. All right, so the temptation is to say, okay, well, come on, I don't like those other values. These are the best values. Let's use these. And no, actually, let me circle in a different color here. Let's just, I'll take the positive square root, and I'll take the arctan angle, and check it out. That puts you over here, which is wrong. So, there it is. You just can't trust those, solve for r, solve for theta formulas. They're just not true. Okay. Now, so what do you do? Well, again, you have these options, and like I said up here, you look at the geometry. Think about the geometry of the situation. So, in particular, I can see that, look, I can view this as being the direction, that angle being 5 pi over 4, in which case I pretty clearly go in that direction, namely with a positive r, to get to my point in question. So I can use these numbers, positive root 2 and 5 pi over 4. Absolutely. And I needed the geometry of the picture to help me out on that, to see that those are the ones that actually pair up. Right, now let me, just for convenience, I think I'm going to pair them up like this. So that has you going a positive amount in that 5 pi over 4 direction. Alternatively, you could also view this as being in that direction, namely pi over 4. But in that direction, well, you're kind of going the wrong direction there, and so you'd have to go, if you will, a negative amount in that direction. Negative square root of 2 still gets you back there to the same correct point. So geometry of the picture, understanding what you're looking at and interpreting accordingly will help you actually find correct polar coordinates. What do you think? Everybody happy with that? Everybody see where the landmine is and how not to step on it? All right. Okay. So equations and polar coordinates. There's several examples here I'm going to run through pretty quickly. This is a pretty straightforward read, I think. What is r? Well, let me go to the highlighter mode. What is r equals 3? That's an equation in polar coordinates. Well, that's pretty clearly telling you a circle. It's telling you the distance from the origin is always 3. That's basically the definition of a circle. Right? Distance from the center being a constant. Okay. But if you didn't see that geometrically for whatever reason, notice you can do this algebraically by squaring both sides using this established relationship and then recovering that now not the polar equation, but now this is the rectangular equation for whatever that curve is. And of course, then we recognize this from high school algebra, circle. Right? So likewise, this. Now again, you could view this sort of, just interpreting from what this says. Theta means that direction. That's theta equals pi over 3. R can be either positive or negative. That pretty clearly gives us that line. But again, if I want to do this algebraically, look what happens if I take the tangent of both sides and then recall this standard relation between the coordinates. Yeah?
Doesn't that mean you have a hole at 0?
Oh yeah, I mean there's an awkwardness there that if x is 0, then this isn't defined, and is there really an angle theta if there's no disk? Yeah, there's a little annoying questions like that. Yeah, that's right. But I don't want to get bogged down in those details. Great question, but I'm gonna deliberately bypass it. Is that fair? Yeah, good. Okay, good thinking though. So notice in both of these cases, what I did in this first step was to look at what I have and then to think about, well, what can I do with, whatever polar coordinates I'm looking at that allows me to automatically convert? And I say, well, r squared. I know how to convert r squared into rectangular. R squared is standard formula, x squared plus y squared. Likewise, tan theta is something I immediately know how to do. So that's what motivates these first two steps. I was aiming for these things because I could convert them easily. Okay. All right. Sometimes no such luck. Sometimes you got to actually brute force plot a bunch of points. And I think it's too tedious to actually do this literally one point at a time. So I like to do sort of ranges of values together. So for example, looking at this equation here, let's think about theta. Various different ranges. I'm going to think first as theta goes from 0 to pi over 2. Those are those angles, 0 to pi over 2. And then let's see here. Well, what happens between 0 and pi over 2? Well, keep in mind, 2 theta is what actually goes into the sine function. So the argument of the sine function is actually going from 0 to pi. And as that argument goes from 0 to pi, sine, we all recall, sine goes from 0 to 1 and back down to 0. Right, so for these values of theta, you might say this is kind of a rectangular plot of this polar equation, if you will. For these values of theta, r kind of goes up and then back down. And now let's think that through and how we interpret polar coordinates for these values of theta. Right, we start off with r equals 0. Then r gets a little bigger for the next angle. And then it gets even a little bigger than that for the next angle. And then it gets smaller again. And then finally back down to 0. And you can see it kind of trace out that curve like that. So it's not exactly plotting one point at a time, but I'm kind of noticing a little over a small range of angles, sort of noticing a pattern and interpreting it accordingly. Okay. Let's real quick think about the next range of values. What happens as theta goes from pi over 2 to pi? Well, real quick, that means that the argument is going from pi to 2 pi, and that means that r is doing that. And weirdly, that's negative. All right, so now we got to think, okay, for these angles here, r is going to start off at 0. It's going to go negative, reach a greatest negative value, and then go back up to 0. So negative for this entire swing. So as I'm looking, let's see, that direction and that direction, and as I'm looking in these different directions, the r's start off. Let's think about that direction. R starts off at 0. And then for the next direction, R slightly negative. All right. And then for the next direction, R is more negative. And then for the next direction, oh, that was terrible. Let me try that again. Yeah, that's pretty good. Next direction, R is less negative. And then finally, for the last direction, R is back to 0. So it kind of does sort of something along like this. Everybody see that? Okay. All right. If you want to carry this through for the remaining values, and this is, I think, a healthy exercise, right? So we talked through those values of theta and these values of theta. Now think it through, if you would, for those values of theta and then these values of theta. And altogether, what's going to happen, I'll just draw the whole thing for you. So it does like this, and then like that we just talked through, and then it goes over and does like this, and then it goes like that, and hooks right back up with where it came from. So that's the eventual picture there. It's like a 4-leaf clover. Okay. A couple more examples. This one works out really nicely. Also, there's just a weird trick on this one. Here, you see this r. You know that r squared is good news. You know you'd like to be able to turn that r into r squared. The very strong temptation there is to say, okay, let's square both sides. And you could. Problem is, cosine squared, what are you going to do with that? All right, so the clever move, wish I'd thought of this. Clever move is don't square both sides. Multiply both sides by r. Then this turns into something that I can immediately convert. And this does too. Right? Yes?
When do you know to multiply by r versus just square?
Yeah. No, it's there is no giveaway. It's just try different things and just I guess you could say not to do it a certain way, because when you try a certain thing it doesn't work out well. Right, but trial and error, roughly speaking. Yeah. Sadly, I wish there was a better giveaway. Yeah. Okay. So in this case, that gives you this equation, and now it's, we have a regular polynomial rectangular equation here, and of course y'all know how to deal with that. I hope y'all remember still how to do that. Do notice that in order to fix this, you have to do this move called completing the square. I hope y'all remember completing the square. It is something I'll say that as long ago as when I was in high school, it was already being swept under the rug a little bit. And that's a tragedy because it's a really important little piece of algebra. So make sure you're good at completing the square. If you're not, you can Google it. I'm sure there's resources out there. But you want to be able to do that because that's what allows you to turn this into a recognizable equation of a circle. Like so. Okay. All right. Okay, next one. This is going to go the other direction. Here we'll start with a rectangular equation and try to find the polar equation. This part's actually kind of easier because in the process you're really just going to plug in the formulas that you have for x and y. So you'll see right there, for example, there's other things going on I'll get to in a second, but y is just r sine theta. And you can, if you want, just take those formulas, just plug them in at the very beginning, and it will work. However, you can save yourself some trouble here and there by every so often it's useful, for example, to go ahead and expand out a square before you plug in your conversion formulas. Because if you do, you might get lucky like we did here, and you might get something that's easy to convert. I mean, in some sense, this has a Pythagorean trig identity wrapped up inside of it. And rather than having to write that all out, not that it's hard, right? But rather than having to write it down, I can just instantly use the much more convenient, noticeable relationship there. So, again, keep a lookout for conveniences. Okay. All right, last comment about these two examples. I want to make sure that you remember these two examples. It is going to happen fairly often, especially when we get into Chapter 5, that a circle centered on the x-axis that goes through the origin and is tangent to the y-axis. Yeah, that's actually, it comes up a lot and it's pretty useful and handy. And so making sure that you know how to do that sort of an equation is very handy. And it won't always be centered exactly at a half and have a radius of exactly a half, but of course you can scale appropriately. And then, likewise, circles centered on the y-axis that go through the origin tangent to the x-axis also comes up. And so knowing what those look like, also handy. Conveniently, it's just sine and cosine. All right, but anyway, you want to make sure to remember those. Okay, so that's polar coordinates. I'm going to very quickly talk about cylindrical coordinates, then we'll go on to the next spherical coordinates, but I'm getting ahead of myself. The good news about cylindrical coordinates is it's pretty much polar coordinates. I mean, it's almost exactly the same thing. In particular, for a given point, you can focus your attention on the projection down into the XY plane. And in the XY plane, we have existing relationships and the rectangular coordinates are represented literally by the polar coordinates. So the first two cylindrical coordinates are exactly the existing polar coordinates. So that's a lot of good news, right? It's really very, very much the same thing with the added detail that, yes, of course, there's also a z-coordinate. And what do you do with that z-coordinate? Well, you keep it. Z is also a cylindrical coordinate, so it's just z is just z. So everything interesting about cylindrical coordinates is polar coordinates. You might say that. So again, reasonably thought of as polar coordinates in space. Questions before I go on to the examples? Okay. So a couple of really easy examples. Notice in this picture that R is distance from the z-axis. Right? And so if your distance to the z-axis is a constant, pretty easy to see that that's a cylinder. Which, by the way, is why we have the name cylindrical coordinates. Okay. All right. Here's a sphere. And recall that we have this existing relationship in polar coordinates. Again, still a relationship in cylindrical coordinates. And so we now have a different equation for the sphere. This is the cylindrical equation for the sphere. I mean, it's just using our existing conversion formulas. Okay, here's the slightly tricky one. This one does get a little bit confusing. I have a favorite point of view on this. There's something very important to notice about this equation. And that is, well, I guess the first thing I'll say is the variables. Here's our variables z and r. And you'll notice that the variables are both cylindrical variables. But the other really important thing to notice is there's no thetas. Theta does not show up in this equation. This equation is independent of theta, you might say. All right, now let me remind you, we considered something kind of along these lines. Oh, that's going to fall. Fairly recently, we were talking about equations of planes, and I made the observation that if there's no y's in your equation, then it's parallel to the y-axis. And I made an argument about normal vectors and stuff. Here's a different point of view on that. If there's no y's in your equation, you can change y all you want, and it doesn't make any difference. So effectively, if you have a point on a surface where the equation doesn't have y's in it, you can slide in the y direction, thus changing y dramatically, but there's no y's in the equation, so it doesn't make any difference. So that's a different point of view on why not having y's in your equation makes your surface parallel to the y-axis. So here, trying to apply that same idea, I can't talk about the theta axis because there is no theta axis, but what I can do is sort of recover this idea of, well, yeah, but just what happens if you change theta? And the answer is absolutely nothing. Nothing happens when you change theta. Theta being not y, y kind of goes this way. Theta goes around, right? So the absence of theta from this means that I can rotate this surface however I want, and it doesn't make any difference. Said differently, no thetas means rotational symmetry around the z-axis. It's a neat observation, very cool to be able to, we instantly have a geometric conclusion about it being rotationally symmetric just by, oh, hey, check it out, no thetas, right? Convenient little observation, powerful conclusion. Everybody feel good about that? Yes?
Is it only ever going to be symmetrical around the z-axis, or will it be symmetrical around like the x or the y?
In cylindrical coordinates, z is a kind of a special axis, right? Because that's the one that theta is measured around. So yeah, this observation really only works for symmetries around the z-axis. Yeah, that's right. Okay, good question. Yeah, so what are we going to do about this? Well, theta doesn't matter, so how about this? How about I just pick any value of theta I want, whatever. I don't know, maybe this one? Not that it matters. Pick any theta you want, and with any theta you want, now let's think about, well, what does this equation look like for that value of theta? Doesn't have anything to do with theta, but z equals a multiple of r is a pretty easy thing to write down. Z is just, that's just a straight line through the origin. So our surface is whatever you get when you take this curve, namely a line, and you rotate it around the z-axis. And I think it's, I'm just going to make a geometric appeal. When you rotate that around the z-axis, you get this cone. Everybody good? One confusing thing about this, some students do get a little stuck on the idea. Well, wait a second, yeah, but I thought R was the square root of that. Doesn't that mean R is positive? And can R? And if R is positive, doesn't that mean Z is positive? What's going on down here below the XY plane? Answer: no. R does not have to be positive. There's no such rule. Okay. All right. So said differently, this point here, I can totally choose to view with a negative value of R. It's a negative value of R where theta is kind of going that way. Negative R and negative Z. Okay. Oh, real quick, this is just a heads up. The world's full of round things, right? And when you have round things, cylinders, circles, spheres, they have a radius, and very often you want to give a name to that radius, right? Whatever the constant value is that represents the radius of that thing. And it's sometimes tempting to use R to represent the radius, right? Good idea not to do that, right? Because you'll notice that now we need R to be a variable, right? Very importantly, R is a variable. It's a coordinate. And so we can't therefore let it also be a constant. So use something else to represent the radii of whatever it is that you're looking at. And you've got various options. If you want to use, for example, capital R, that's totally fine. Or some people will do like R naught. That's fine. Of course, you can also just venture out into the other areas of the alphabet and use A, B, C, whatever. There's plenty of letters. But don't just use just R by itself. Okay. Yeah, was there a... No? Okay. Yes?
I'm
yeah.
kind of confused because I thought that R kind of did represent like the radius.
Well, it is a radius in a sense, right? It's a distance away. So it's a radial distance away from something, right? Away from the z-axis. But what I'm saying is, if you have, for example, if you were to have let's say a sphere here, right? And you wanted to talk about what is the radius of that sphere. You can't call it R. Because R is, looking at the point on the sphere, R is this distance. And you can't just choose to set the constant blue distance there equal to the highly variable purple distance. It's just a confusion of variables. Yeah. Is that satisfying?
Yeah.
Okay. Cool. All right. So let's talk about spherical coordinates. Some of y'all have seen spherical coordinates before. If so, great. If not, don't worry. I do want to fix one thing right off, and that is a lot of people think of spherical coordinates also as being polar coordinates in 3 space. I think that's a problem. For one thing, we already decided we were going to call this polar coordinates in 3 space. And it really is very strongly polar. I mean, it's very closely connected to polar coordinates, right? So you can't use the same name to talk about 2 different coordinate systems right off. Right? Secondly, there are some very important differences between spherical coordinates and polar coordinates. So I think it's a mistake to think of this as being polar coordinates. Now that said, the first coordinate that we're going to talk about is familiar. Theta. Theta it's the usual theta. It's angle measured counterclockwise from the positive part of the x-axis. That's where the similarity ends, pretty much. Anyway, let's go on. So that angle, you'll notice, defines what I'm going to call a half plane hinged on the z-axis. And by hinged on the z-axis, I mean that the edge of the half plane is the z-axis. And as theta changes, you can think of these theta half planes as being kind of like a door that swings, where the z-axis is the hinge that the door is mounted on, if you will. Okay, so there's our theta. Okay. All right. Now, next coordinate. Next coordinate is called phi. This is another letter of the Greek alphabet, spelled like so, pronounced like that. So phi is another angle. It's measured from the positive part of the z-axis toward the theta half plane. So remember, we have a half plane that's defined by the angle theta. Right? So when I say toward the theta half plane, what I mean is positive values of phi go that way. Not back this way. Right? Not in some other random direction. Right? But toward and into the theta half plane. Okay. Now, again, of course, it's perfectly allowed for certain angles to be negative. And this is such an example. Phi is perfectly allowed to be negative, and I'm going to say exactly what you would expect if this is phi equals 0, and if positive phi's go that way, kind of like you might expect negative phi's are just going to kind of lean backwards. So negative phi's just lean back the other direction, exactly opposite of the theta half plane. Is that cool? Everybody's happy? Okay. Yeah, okay. All right. So, okay. Well, so we've got two angles here. We've got our theta and our phi, and I'll observe that between the two of them, they define a direction out of the origin. Right? There's exactly one direction from the origin, defined by a given theta and a given phi. And with that direction defined, the third variable, rho, and I know it looks like a p, but very importantly, it's not a p. Oh, and please do be very careful. Please don't write it as a p. It's importantly not a p. Greek letter rho. So, by the way, if you haven't, understandably, haven't spent a lot of time writing Greek letters, if you haven't drawn rows before, and if you're not accustomed to how to write them, you might have to pull out a piece of paper, and it's a little humiliating, but you might have to actually sit there and practice, like you're in second grade and learning how to make your letters, right? I did it when I was in college, right? I filled up most of a piece of paper, practicing and kind of getting a finger feel for how to make various different letters that I was going to need to do. And by the way, there are much harder Greek letters that you're not going to need in this class. But anyway, okay. So rho is, I'm going to say how far in that direction. And again, I had to, just like with the polar R, I have to put that in air quotes. Right? Because, it's a coordinate, not a distance. Remember, distances are intrinsically positive things. Rho is not. Rho can be negative. And if rho is negative, just like you would expect, just like we did in polar coordinates, they just go backwards. Same direction, just backwards in that same direction. Go the exact opposite direction. Okay. Everybody good? So rho, phi, and theta. All right, these are the spherical coordinates. This triangle right here is going to be particularly important. I'm going to recopy it. I guess I have to jump out here for a second. I'm going to recopy that triangle because I personally find it a little annoying that I'm not looking straight on. I'm looking kind of at some weird angle. I'm looking kind of from the side and from above at this triangle. I mean, after all, look at this edge right here. That edge right there that's kind of pointing downward, that's horizontal. Right? It's just weird. It's hard to see straight. So I like to give a looking straight on direct view at that triangle. So I'm going to look at this picture, but don't forget this is just a representation of that picture in 3 space that we're actually interested in. Okay. So that said, a couple of neat observations to make. That angle is phi. That means at that angle also phi. This distance is rho. And with that in mind, I can now just start doing trig. And the first little bit of trig that I want to do, this thing over here, r, it's just rho sine phi. Nothing to, it's just a trig of this little triangle, aka this triangle up here, right? But the trig of that triangle tells me that r is rho sine phi, and that's awful handy because knowing that r is rho sine phi allows me to recover previously established formulas. So x, I already knew that x was r cosine theta and y was r sine theta. So we are now 2/3 the way done with our spherical coordinate formulas from this one little observation of trig. Right? So r, from this picture, r is rho sine phi. So x is, well, it's r cosine theta and y is r sine theta. Just r is now rho sine phi. Everybody good? And then, of course, this is z. It's the other side of that triangle, so rho cosine phi, and that is our third coordinate, and that completes our conversion formulas. What do you think? Everybody happy? Okay. All right, so I'm going to give you 2 bits of advice related to these formulas. One is make sure to understand all of this reasoning that gets you to these formulas. If you memorize those formulas, the time will come. I don't know when. It might be, November. It might be 10 years from now. I don't know. Maybe you have a lockbox of a memory, but I certainly don't. But at some point, if you memorize these formulas, you're going to get them wrong. You're going to get confused, and you're going to think rho cosine phi instead of rho sine phi up here. And you just spaced, and you just got it backwards. So it's very important to understand the picture and the resulting trig that gets you there. And I emphasize, look how easy that picture is. It's a really easy little picture. Related, note, in my life, I have never memorized these formulas. And I've done a ton of spherical coordinates. Just tons and tons. When I need these formulas, I think about this picture, and I'm like, wait a minute, which way is it? R is rho sine phi, that's right. And then boom. So easy. Right? So it takes me 3 seconds every time I need those formulas. Okay, so that's my first bit of advice. Make sure to understand where they come from. My second bit of advice is go ahead and memorize these formulas too. Right now, not that you can trust yourself with it, but that's not that bad. Sort of right before the exam, perhaps. Right? Make sure that you know these formulas, because if they come up on the exam, then that saves you a few seconds, and it's a double check on whether you thought through the trig correctly, and I might as well do both. And yeah, sure, that's going to fade. That memory will fade. Whereas the concept won't, but still better than nothing. Okay. All right. Pretty easy observation to make about rho, that it has this sort of Pythagorean relationship with x, y, and z. And so notice then that if you let rho be a constant, then you get the equation of a sphere centered at the origin. Again, very simple equation for a sphere, thus the name spherical coordinates. Okay. All right, next thing I want to talk about. And let me zoom back out. Y'all will recall with polar coordinates we had a uniqueness problem, right? So there's kind of, in some sense, two different angles. Like if you want to get to a point down here, there's this angle. Positive R in that direction will get you to this point down here. But also that direction with a negative R will get you to that same point. So there's kind of two different angles. And of course, yes, there's also plus 2 pi. Plus any multiple of 2 pi. Yeah, sure. But that's always true, and so it's kind of never interesting, and so you have to put it on there sometimes. But let's focus on the full turn aspect of things here. Okay, so in some sense, two different polar coordinates for a point. It's going to turn out that there are 4 different spherical coordinates for a point. And roughly speaking, it's because there's 2 different thetas, and then for each theta, there's 2 different phis. Pretty much. So let's think that through. Here's a point. I'm going to leave the details for y'all. It's a good exercise to think through those details, the trig and such. But with that point there, you can think of theta as being pi over 3. Like that. Or you could, and this seems weird, but you could do an extra half turn, right? And think of theta as being 4 pi over 3, right? And so you might be thinking to yourself, wait a minute, that's going the wrong way. How would I get a direction that's this way if I'm in that half plane? And it's with a negative value of phi, right? So again, phi is measured off of the vertical. That would be if we're looking at that theta, this would be positive phi, and that's just negative phis. Right? So both of the values of theta work. Just different phis. And then now, so now that we've established that you've got 2 different. We've got 2 different thetas that work. Let's think about our phi options. So yes, you could have a negative phi like this, or you could also have a positive phi, which gets you going exactly the wrong direction, for which you would then simply have a negative value of rho. Does that make sense? Yes.
Is there any domain for the theta? For example, do we need to write theta then equals 2 pi, 2n pi at...
I'm sorry, I'm just not understanding your question.
Is there any domain for the theta?
Domain? Yeah. So like allowable values?
Yeah.
No, so theta is allowed to be any value. And phi could be any value as well. Now, there are values of theta that are more commonly used and more commonly useful, right? But theta could just go around. I mean, it would be kind of weird, but you could conceivably just go around a bunch of times and then stop, and that defines a direction. Yeah. Yep. And then what I'm doing here again, I'm ignoring full turns, right? And I'm just considering the fact that there are for example, still 2 importantly different. Like this value of theta there is importantly different from this value of theta here. Right? Those are not full turn different. Those are only half turn different. So they're not just different numbers, they're different directions. Right? So these are the ones that I'm focusing on. But yeah, you can add as many 2 pi's as you want. Yeah. Yes.
Suppose you keep theta the same. Suppose you vary theta and keep phi the same. Would it be possible to manipulate rho to make it negative to get the same point, or does rho always have to be positive?
Rho does not have to be positive, and yeah, so sometimes it has to be negative. So, for example, here's one that I drew a minute ago. If we take this value of theta, right, and then if I choose phi to be, like this, kind of this way, whatever that angle is, I guess that's 3 pi over 4. Right? So this is now pointing sort of, the picture is a little hard to see. It's going into the board per this dark green, right? But then down. So it's like it's down that way, right? Then, you would have to use a negative value of phi. Oh, and I didn't draw that very well. Let me try that again. I need this to be, there we go. How far would you have to go in that direction to get to this point? Well, you'd have to go a negative amount in that direction. This is going in some sense exactly the wrong direction. And so a negative rho is what gets you back to the point where we want. Yeah, cool, yes.
Is there one you want to try and keep positive since you can manipulate all of them? Is there one that's easiest to keep positive?
I'm going to answer a related question, which is there a sort of a natural sort of best set of values of these to choose? And yeah, sure. And we're going to encounter that later on when we get into chapter 5. But for the moment, I don't want to reveal what my preferences are, because I don't want my preferences to come off as arbitrary or lazy, right? There's really good reasons why we're going to want to restrict certain values. And I want to show you the reasons before I show you the answers. So for the moment, rho, phi, and theta, no rules. They can be anything. All right. Okay, so there's a couple of neat applications of this. Let's see here. So spherical angles and longitude and latitude. I think this is neat and fun. So let's observe that if you set up the Earth correctly, set the Earth with its center at the origin, the prime meridian on the positive part of the x-axis, North Pole on the z-axis, etc. Then theta is longitude, east longitude. They're exactly the same. That's neat. That's handy. Very convenient. What a coincidence. And then, now let's talk about the phi. Phi is this, and phi is not exactly latitude. Latitude is like that. Right? But what you'll notice is that north latitude and phi, they always add up to pi over 2. So there's a very strong relationship then between the spherical angles and map coordinates on the Earth. And then I suppose there's a little matter of what is rho. Well, rho is always the distance to the center, namely, in this case, the distance to the center of the Earth. It's always the radius of the Earth. There's some number, whatever that value is. So a pretty cool relationship. A really nice application of this has to do with this question, which is if you have 2 points on the globe, and you want to compute the distance between those 2 points. So let's suppose x2 here is Durham, and x1 is Sweden. What's that? Stockholm, whatever. I got all my Scandinavian geography confused. So we've got 2 locations. What is this shortest distance? And it's certainly not a straight line. There's no straight lines on the surface of the Earth. Temptation to say, look at the Mercator projection. No. Mercator projection is highly distorted. It's useful in certain ways, but it's terrible in other ways. Side note, all flat map projections of a not flat surface, they're all bad in some way or another. But side note. So how do we actually compute that distance? And the cool observation to make is that distance is very easily related to this angle. That angle is the angle between 2 vectors, right? And those 2 vectors, I know how to dot to relate to that angle. If only I knew their rectangular coordinates. So how am I going to find the rectangular coordinates of Durham and Stockholm? Well, I can find their rectangular coordinates by knowing their spherical coordinates, which I can get to because I know their longitude and latitude. So it's quite a connect the dots, and I left out the details because the details are details. You don't want to get lost in that. But map coordinates tell you spherical, which tells you rectangular, which allows you to compute the dot product, which allows you to solve for the angle, which tells you the distance. And so you can compute the distance along the surface of the Earth pretty straightforwardly. A little bit of trig, right? But pretty straightforward otherwise. All right. Okay. This last example here is very similar to what we did in polar coordinates. You just plug in. So, for example, x is that formula, right? You're just plugging it in. Do be on the lookout and try to take advantage of when you can can save yourself the trouble of dealing with a bunch of trig and trig identities by noticing something like this coming up. That's a time saver. And then you have yourself a spherical equation. You've converted rectangular to spherical. Okay. Okay, so we didn't quite finish this. So there's some things to say about standard basis vectors. Is today Wednesday? It is. Oh, man. Here's the good news about standard basis vectors. And I will say some stuff about this on Friday. But the good news is that there's very little you need to know about standard basis vectors and other coordinate systems. Rectangular standard basis vectors are good. Non-rectangular standard basis vectors, we're really not going to use them much in this course. And you can write down formulas for it. They're just a matter of looking at the picture and thinking about the geometry of the picture and writing them down. They're not that hard. It's mostly just kind of little geometric puzzles. So I'm going to suggest that you look at these and persuade yourselves that these formulas work, and make sure that you know that these things exist, but don't expect that they're going to come up much in this class because they really aren't. Okay, and this is just a couple of warnings, so we don't need to spend time on that. So I'm going to declare us done with Chapter 1, and we will pick up here on Friday. See y'all later. Okay.